Welcome to the last section of Chapter 2. And in this section, we're going to be studying infinite sets. So within this lesson, we're going to be able to define an infinite set, show that a set is infinite, get a general term for an infinite set, and define countable and uncountable sets. So a set is considered to be infinite if it has a one-to-one correspondence with a subset of itself. A lot of technical meaning there. So, if I want to show that this set is infinite, I need to show that the set 5, 10, 15, 20, so multiples of 5 is an infinite set. So, in one way to put this into correspondence with a proper subset, so if I think of multiples of 5, the subset of that would be multiples of 10, because multiples of 10 are also multiples of 5. So if I can line them up and have one-to-one correspondence, so 5 goes to 10, 10 goes to 20, 15 goes to 30, and we see that there's this nice pattern, then that is an infinite set. So the fact that the list of multiples of 5 is infinite doesn't actually relate to whether or not the set itself is infinite. So the general term for an infinite set would be generating that 2n formula we just did in the other problem. So the pattern was 5 mapped to 10, which was 2 times 5, 10 mapped to 20, which was 2 times 10. And so that's what we're talking about when we say general term. It's almost like a formula that would map it from one set onto the other. So if I have this set, and this set we can see is being generated by adding 3 to each term. So once I find the pattern, then I can say that it increases by 3. So when this is the case, 3n is a good choice, as n would increase by 1. So if I had 3n, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. But that doesn't quite get me to that set, right? So my set was adding 3 each time. So I'm not going to get a 13 from doing 3 times something. So what I could do is say, well, that's close. I'm almost there. I'm just 1 below where I need to be. I need to be at 4, 7, 10, and I'm at 3, 6, 9. So I'm just going to add 1 to that, and that will put me in the proper set. So a countable set is a set that is finite because I can count the number of terms. If there are too many terms to count, meaning it's infinite, then it is considered uncountable. So if I want to show that a set is countable, if I have this set of all integers, integers is not a finite set. So I need to find out if they have a one-to-one correspondence. Remember, it's not the number of items that makes it an infinite set. It's that one-to-one correspondence. So if I think about the group of natural numbers, and I map that group of natural numbers to integers that are 1 less than them, I can see that every integer will eventually get matched with a natural number, which gives us that nice one-to-one correspondence. The proof, however, would be stronger if we could get a formula to generate that. So this is the example of the formula that generates the last example. In ALEKS, it's not going to ask you to get this high level. It's just going to ask you if a set is countable or not. So that's what you really need to focus on coming away from this solution.